Okay. Hello, everyone, and welcome here to Go to 10 for our AI skilled session. Warm welcome. And my name's Aaron. I'm the community and event manager here for Food Cafe Linköping. And this is the start of our AI skilled series. And we're very, very happy to have Elliot here, who is going to be leading us on our first session with AI skilled. And yeah, very excited to hear what he has to say. Elliot has been here quite a lot. He's very active here at Go210. And I'd like to give Elliot a warm welcome today. So, Elliot, it's all yours.
Thank you very much, Aaron. Hi, everybody. Good to see some people here. And the topic of today is, as I'm guessing most of you knew, foundation models, especially foundation models beyond LLMs. But before we get into that, I'm going to do something possibly kind of stupid because we're in Sweden. That is, I want to do a small poll of the room. What is AI in the first place? I like to do this when I have the opportunity, and you're stuck in a room with me for a little bit, which gives me opportunity. So we're going to give us a few options. We're going to raise hands. Yeah, we'll figure it out. So if we start with the calculator, everybody who thinks a calculator counts as AI, please raise a hand. Okay, so nobody in the camp of AI is calculator. Second up, we have like Google Maps, right? Is Google Maps AI? We're getting some points for Google Maps being AI. Okay, I think that's cool. I dig it. Then we have like a chess bot. Like it solves chess really well. It's hard coded by some engineer somewhere based on rules they think are good for chess, but it plays chess well. Is this AI? Yes, we're seeing like monotonic increases here at least. So it seems like I put them in the right order. How about a more general computer system then? We can give it any game we like, essentially, and it gives us a good solution for it. Is this AI? Yeah, you can give it a game, you can give it a description of a route maybe. Give it a map, tell it to find a path. Give it chess, tell it to find the solution. The trickier it is, maybe it takes longer time, but whatever you like, really. Is this AI? Okay, I think we're nearing majority voting. How about these like image classification systems, like the cat-dog classifier, right, is the classical one, or anything like that, you know, video surveillance stuff, for example. Okay, we're seeing some. And for our last vote of the day, how about this like Gen AI wave? Is Gen AI AI? I'm happy to see if it's not. Okay, we do have 2 people saying it's not. That's cool. I like it. But for the sake of today's topic and presentation, I'm going to be drawing a line around there, and I'm going to be calling the bottom side of this AI for today. And we're going to be looking at a few representatives of each of these categories, how we can use them, foundation models in their area, and what the point is. But with your mandated, contributions to my existence done, the mandatory who am I and why should you even listen to me about any of this slide. So I'm Elliot, as we mentioned before. I don't even think my name is here anywhere, but I'm Elliot anyways. Studied civilingenjör here at LEU Y, applied physics and electrical engineering with a master DAMI in data-driven analysis and machine intelligence. Makes for an abnormally long title if I say it all, but that is it. These days I'm a PhD student, still at Linköping University, and I focus on a particular type of neurosymbolic AI. Not going to get into now what that type is, because I made these slides, so we're getting back to my favorite topic later. But that is what I do as a day job, and I've been doing that for about 2 years at this point. Also do some non-profit organization. Particularly, I help out with RoboCup Junior, which is the youth championship of robotics. We're the national organizer. So if you or your org or whatever want to get involved with that, do let me know. I love talking about it. It's super cute. Youth in Sweden up to 19 coming here to Linköping, competing in robotics. But perhaps the most relevant point for why I'm here talking about foundation models is that I've done consulting for quite a while. And these days I do that through a company called Ellery AI together with some friends of mine. But what we mostly do there and what I've mostly done before are these smaller scale AI proof of concepts or MVP systems. And if you're doing that, right, you don't want to spend more time, more effort, more work on something than you absolutely need to. And that is where I've been mostly using foundation models. No point training your own thing if you don't have to. So some of those lessons are what I'll be bringing up today. But, well, speaking of that, what are we going to be talking about more concretely? Obviously, it's foundation models. And when I say that, I generally mean models which have been trained by other people, but which are general enough that you can still use them for a wide range of applications. Language models are obviously the common suggestion and the obvious thing you have in mind, but there are a lot of other fun things which we'll see. However, it will be a flyby overview of a few different types of foundation models, each of which I could do an own session on, but we'll look through a few of them. We'll see the most important things to keep in mind with their particular types, and we'll see a few examples of how you could use them, hopefully. We'll do questions as we go. So if you have any thoughts as I'm saying anything, please do raise a hand. If I'm not seeing you raise a hand, shouts at me or throw a nearby shoe, whatever you prefer. And yes, I'm hoping that should do it for us. So to get into this first, how do we usually build something with AI? Anything really? Well, I see sort of two options. The classical pipeline is what most people, most companies, most businesses have in mind. And you start with getting your hands on a model, right? That's usually a good way of doing with AI. You start getting some engineers, you start getting some data, then you do some coding and you train your models on this data which you got. You evaluate the model, and then, well, it turns out it usually wasn't good enough initially, so you revise and you do this pipeline a few times. The more you do it, the better it gets. And hopefully you knew roughly where you wanted to go when you started. This can be a bit annoying, can take quite a bit of time, but at the end you get a model fit for your needs. Once you have that right, you want to use the model. So you have your model, you put that into some form of application, and hopefully it spits out value for you, right? Depending on what it is, this is all going to look different, but this is a rough pipeline you usually go through. So I'm here to talk about foundation models, right? So of course I have a foundation pipeline, which I'm suggesting you use instead. And now instead of making the model, you still need to get a model, right? If you want to use one. But step one here is instead you do choose the type of model you think you'll want. And there are a lot of types of foundation models out there. So you pick what will be useful for your circumstances. This is one of the things we're going to be talking about today, seeing an overview of a few different types of foundation models and what they can be useful for. Then you just browse your options online, usually Hugging Face, and then you download them. Much easier than actually having to train them yourself. And when something new shows up, you can just download that new model, and hopefully, and usually, it's drop in and replace for your old model. So there shouldn't be much need for revising and training on new data and such as you go. Once you have it, the usefulness of it remains the same. You plug it into your application, so. But all right, so this is the sort of general overview look that we're going to be looking at. I promised looking at a few types of models, so that's what we'll be doing next, an overview of a few different types. First of all, we have the protocol child, right? We have the large language models. I'd say we're going to go beyond them today, but we're still starting out with something nice and familiar. As a lot of you might know, these were introduced the concept of attention into language modeling, which means that the model can handle really long pieces of text by, at runtime, thinking about what matters, essentially. And I'm anthropomorphizing these more than I probably should. But yes, so when you give them a text, they can figure out live what matters. They don't need to know ahead of time while they're reading the text what you're going to be asking about later. And that makes them really good at handling a whole lot of text. And what people usually use these for is autoregressive text generation, which means that you give it a piece of text and then it writes the next word. Really, it's operating on subwords and stuff like that, but let's not get into these details. And by doing this autoregressive generation, you can get it to write text. And I'm sure all of you have tried some LLM thing. Yes? Seeing nods. Cool. I would be surprised if not, given the place we're at. But there are two interesting things to note with these models, especially as it comes to the sake of foundations, and that this training is usually done in 2 phases for them. The first is you do pre-training, which is where you scrape the entire internet, or as much of it as you can get your hands on, and then you shove that through the model to make it learn general concepts. It learns language, information, and all of that which you want it to be able to do. But it still really acts just like text, right? The second phase is what's called RLHF, reinforcement learning with human feedback. Here you make it write text, and then you show that to your human, and the human says, yes, I like this, or no, I don't like this. And in that way, we get them to behave more the way that we want, which in this case, almost always is instruction following. So we give it instructions, and then we see how well it follows those instructions, and then afterwards, it follows them better. And by doing this for quite a while, we get a system that is capable of following your instructions. And when you're looking at models, you can usually find either of these 2 variants, with the pre-trained only version being called base or something like that, and the RLHF version usually being called instruct, whatever. So usually you just want the latter, but if you're doing something really strange, I guess you might want the former. So again, I think a lot of you already know these kind of topics, but I figured we'd mention a few of the open source models that are out there that you could download right now. Here are a few you have, which are sort of topping a few leaderboards at the moment, right? You have Qwen, V3 is the newest, you have Llama, which is at 4 at the moment. DeepSeek is at a 3rd generation, and of course, GPT's own GPT-Oz. All of these models, as well as essentially all the models we'll see later, usually exist in a few different varieties of different sizes and so on. When you pick them, bigger is usually smarter, at least within the same model class and family. So you'll get better performance at the cost of needing more hardware, more compute when you run it. There is also a second thing in addition to this, which is what's called quantization, which means that you remove the detail essentially from the model. This makes it easier to fit and faster to run as you go. But as said, it comes at the loss of some performance. What fits you best as you go, you sort of need to test it out, and it depends on your particular constraints. But now I'm again going to do something maybe foolish in Sweden, and I'm going to ask a question to the audience, but you're not so many people, and I can hold you a bit hostage with not going on. And that is like, what can we do with these models? I'm curious to hear any idea from the audience on what sort of interesting applications we could build using LLMs. We're starting with the easy one for you guys. It's gonna get harder. So anybody has a cool idea of any application you could build with LLMs? Could be a new thing, or could be something that you've already seen.
Okay.
Obviously a chatbot.
Chatbots are great. Sick. Any other cool applications that we can do than just pure chatbots?
You can ask it to analyze your bank account CSVs and suggest what did you do here? Where did you buy this? What type of cost is it? I've done that.
Nice. So we could build like an automatic like budgeting kind of tool to give financial advice to people. That would be sick.
You could build like an archive system where you could say you're like me and you have voice notes and scribble notes and type messages. You can upload them, say an image of my text, and have one read it and then actually store it for you in a database somewhere. The same with like voice to text. It could text it out for you, store it in a database so you can organize it.
That sounds brilliant. So we could have like our own little library of our own stuff, right? Super convenient and a good way of synchronizing our information from all across the spaces. We've got it. All right, cool. I think 3 is a good number, right? So let's move on and have a quick peek at some other kind of models out there. Still staying on the more well-known stuff, right? We have diffusion models. And these I'm also guessing most people have heard about. And what they do is they incrementally denoise something, just like we're seeing here on this image. It started out as a whole bunch of noise. And then the model has been trained to remove these noise incrementally. And as it does that, it manages to recover an image. And by steering and controlling the way this denoising happens, we can control what image we get out in the end, and so on. During training, these have been trained in the inverse direction. So you've taken an image, you've added a bunch of noise to it, and then you've removed the noise during training. And while you use it at inference, you give it pure noise, and you essentially tell it, hey, I promise you, there's an image of a robot holding a flower under this noise somewhere. Get it out for me. Then the model does its best attempt at managing to figure out where the noise is and what the original image is. You remove it, and you recover the image. What I've been saying now is image, I think probably, I don't know, anybody count 15 times, something like that in a row. But it's not only images, right? You can denoise a whole bunch of stuff. Anything you can add noise to, you can remove noise through, and you can get this system back. For example, we're starting to get video models, right? Which is sort of images stacked on top of each other. But we can also denoise synthetic data directly. We can denoise text-to-speech, and we can denoise a whole bunch of stuff. Good save there with me not coming up a third thing at the top of my mind, right? And there are some cool things to keep in mind, and that's especially that there are lots of control options for these ones when you use them in practice. First of all, you can do what most people have probably seen and probably tried in painting, where if we consider we had this image, and we assume it wasn't just noise at the moment, I could have timed this better. We remove a small portion of it, and then we ask the model to just fill in this part. And then it will do that based on the context around it. So this way, we can take an image which we have and change parts of it. We can also do outpainting, which is essentially the same thing, but we go along the outside of the border of the image, and we make more image along the edges of it. Lastly, we have the concept of control net, which is super useful. I again won't get into the details of what this is and how it works, but it lets you fix a lot of control information. For example, you can fix the pose of a person and guarantee that it will be the same pose even when you change other contexts around it. You can fix colors, poses, orientations, and so on. There's a whole lot of stuff you can look at and that you can fix between the different generations. Again, we're going to take a small look at a few different diffusion models that are out there and what they diffuse for us. So the first one is stable diffusion, right? This is the one most of you have probably heard about. Some of you have maybe even tested. And generally speaking, it diffuses images. We also have one which is currently, which does video generation and seems to be very good at the moment. You have like Supertonic, which does speech diffusion, and that one is even optimized to run on mobile devices, so that's pretty cool. And we, as said, don't need to stop at these like more standard things, right? So we have like Huanyuan 3D, which does, as the name suggests, 3D assets of all different types, everything from whole 3D worlds to 3D objects to 3D characters. So all of these you can use for a whole array of interesting applications. And maybe you're starting to get the gist of this now. What kind of interesting applications can we do with these? Hello, audience. Good to have you here again. So we're getting on to slightly more obscure models. What can we do with diffusion models? Any cool suggestions?
Yes.
Okay. So I used to work at Ericsson, and then we had point-to-point radio communication, microwave, and then you have to denoise the signal. I'm not sure if you can get a model up to the real-time speeds that are needed, but that's an idea.
That's really cool. Possibly you could. Diffusion models in general are kind of expensive to run at runtime, right? Because to denoise an image like this takes usually a lot of incremental cost. We remove some of the noise at each step. But it's quite possible you could do something really cool like this and be able to get it up to speed.
I guess especially if you can accept lag or, lower latency, so to speak.
Then I absolutely think you could. And it would be pretty sick. Yeah, go for it. Just 1 second. Yeah, so mic is because we're recording this, and it's good for the recording to have mic stuff.
I might be behind because I didn't know there was a model that could do 3D. Is there a way, like, say you broke a part somewhere, and it's just a little plastic part, and you want to make that part again? Could you, like, take a picture of it with the 3D model, and then it could generate, like, what you would need to print that part again for a certain 3D printer?
Yes, you could. So, for example, this Huanyan, which I showed here, I know it supports image to 3D. I think it even supports multiple perspective images to 3D. So you take photos of around it, then it gives you a single 3D file. The file it gives you is usually in GLB, which is like a 3D format. Then you can take that and you can put it in your 3D printing software, and then that does the 3D printer specific stuff for you. And then, well, you could print it out. Probably you need to play around with scale to get that right, since you often lose scale in pictures, right? But that should absolutely be doable and would be actually super cool now that you say it. We can do our own automatic home repair system thing. Sick. Any third suggestion from the audience? Yes, good. I thought I saw you move before. Good thing if I stare at people long enough.
Yeah, I was thinking a bit about it, but it was replacing government. So basically extracting some relevant features and then figuring out what's best for everyone.
Okay, that is spicy. Okay, so we're going to do a generative diffusion-based government structure. I've seen diffusion models used for policies in robots and decision control at that level. Doing it at cityscape or country level would be really cool. I mean, we see this used, for example, for weather predictions. You can do like this, right? So you could, if you have maps of populations and such, especially if you have maps of populations and movement conditioned on certain properties, maybe tax laws or environment or agriculture or whatever it is you're interested in, you could probably train a diffusion model to adapt based on these behaviors. And since they are easily controllable in that you can, of course, start with an image, add some noise to it, and then remove it. Or in this case, start with a country and the population in the different cities, add some noise to that and tell it to remove it based on this new policy. You could see how some stuff turns out. That would be sick. I'm not sure how much I would trust our new diffusion-based overlords, but it would be a lot of fun to see what they decide to do with us, at least. Cool. I assumed you would say something like, I don't know, like anonymizing images and replacing faces of people with other realistic faces. I mean, you come from a police background and stuff, right? But yes, AI government overlords is also cool. Much cooler, actually. Okay, so I don't think we should stick with the overlords anymore in case some Silicon Valley tech pros hear us. So let's move on to embedding models. And these are actually my favorites. So we're going to spend a bit of time here and do some demos and stuff. What these do is that they take concepts and they represent them in 3D space, essentially. Except that the space is in 3D space, it's like 1,000-dimensional space. Because, 3D space is never enough. But to get a feeling of what I mean when I say representing concepts, we have this little image. Can you read this from where you're at? Yes, cool. Okay, so what this tool has done is it's taken one of these like representations of language which have been learned in, I believe, like, let's say 1,000 dimensions, and then we've compressed that down to 2 dimensions so that we can look at it. And then we've selected some particular words and some particular word pairs to look at. So along this axis, we have she to he. The more similar to he a word is, the more it's going to be on this side. The more similar it is to she, the more it's going to be on this side. Down here, we have family. Up here, we have work. You get it, right? The more similar to family it is down here, more similar to work, we move up there. And all of the words here which we're seeing paired are, for example, niece and nephew. And these pairs have been done manually, right? But some of the other pairs we have here are like daughter and son, aunt, uncle, grandmother, grandfather, and so on. Even non-family things like actress and actor, queen and king. And what we see, right, is that in this embedding space that we have, the step between these is pretty much the same. So we see that this angle which we take is very, very similar across all of these. So if I had a word, let's say I knew what mother was, right? But I want to know what is a male representative, male equivalent of mother? Well, I look at a whole bunch of pairs like this. I find this little vector to go along. I start there, I take a step, and I wind up close to father. So in this way, we see that the embedding space has learned to represent these words, these concepts, the way that they are like semantically meaning, right? And we can also see, for example, that being a niece is apparently more family than being an actress, which makes more sense, I think. Apparently being a woman is more work than being a mother. I'm not sure that makes sense. It's also more work than being a queen, which maybe that's true, actually. And in this way, we can get so much information from different underlying spaces. And I'm now considering if we do the demo now. Yes, let's do the demo now, because I think the demo is cool. So this cable didn't like me before. We're going to hope it works, and I'm just not going to touch anything more than I need to. We just looked at a representation of words in 2D space, where we had he and she, and the work and stuff. This is 3D space, and the angles here are just chosen to essentially spread out the words as much as possible. So they're not aligned with any particular words. And when we have this, we can do some fun stuff. Anybody in the audience, tell me a word, your favorite concept. Somebody, come on. A dog, good choice. Okay, so we're gonna do dog. We can search here for dog, and then we can see some stuff that winds up being similar to dog. We see we have dogs, cat, cow, rat, are all similar to dog, right? So if we were looking for concepts similar to dog, we could find this. You also see some other stuff which is interesting, which shows up, like breeds, for example, and catcher, which, I mean, yeah, you have dog catchers, you have dogs which catch things, you have dog breeds and such. And while we see that these are the highlighted dots here, they do seem kind of spread out and far apart. That's partially because we're seeing like a 3-dimensional representation of this 1,000-dimensional space. So in the original space, they're actually closer. Any? Yeah. No, it's perfect. Love questions.
So all of those dots represent like a connection to dog?
Yes, so all of the dots here are different words.
Right.
And all the ones which we see highlighted are just the ones that are close to my cursor, I think, on here. But here we see different words, and we see how close they are to dog, essentially. So dogs is 0.4 close to dogs. Cat is 0.757 close to dogs, and so on. And higher is further away, it's distance. Do you have another word you want to try, by the way?
Crocodile.
Crocodile, let's go. Do we have? Okay, we don't have crocodile. Too bad. It's not funny enough set of words here. They've got bad choices. not Texas enough. Texas have crocodiles? I don't know. Okay. Cat. We can do cat. Catholic. But let's do just cat. Maybe. Come on. Yes. So we see it's similar here, right? We have cats, we have dogs, again. We get to pets. We have mouse being very close to cats, because, I mean, where else would the mice be if not close to the cats, right? Somebody needs to keep track of them. Don't ask me what lovers is doing here. That makes sense, I guess. If people like cats, I like cats as well, but yeah. And we see a lot of stuff here. We see toys, we see hat, black cat, right, stands out as a thing, and so on. But let's keep with this animal theme and actually try out one word I had in mind, and that is fish. So we're going to do fish, and we're going to do, hope I remember how to do this, we're going to isolate just the 101 points which are closest to fish. So now we see these are the 101 concepts closest to fish. And we're going to do a fun thing, which is TSNE. So what we're seeing here is one way of representing this 1,000-dimensional space. We're going to try a different way. We're going to swap to this. And what this does is that stuff essentially tries to push itself away from other concepts. And the further away it is in the original space, the harder it tries to push away from the other ones in this low-dimensional space. And these are going to keep going until we stop them. But I'm going to hope that this is a good spot. And now we see that we've sort of got two clusters here, I hope. And we see we have one set of here where we have fish, we have sea, wildlife, river, exports, mineral. So we have a lot of like natural concepts, along with cattle, goat, dogs, creatures. So we have that sort of meaning of fish has been sort of captured in this lump over here. Taking a peek at this other set which we have here, if I can manage to do it, we instead see foods, vegetables, milk, pork, soup, juice. Because, I mean, fish, right, in difference to cats and dogs, is the thing you also eat. So we wind up having these close together as well. But while viewed under this TSNE lens, we see that these separate into two different groups, where we have the food group and we have the sort of natural wildlife group. And I think that is super cool. And using this, right, you could then, now that you find sort of where this cluster is, you could also, if you get a new word, you could figure out, hey, is this like a food or is this like a natural environment thing? Pretty sick. But let's get back to the main topic at hand. And yes, if you're interested, we can play around more with this later. You can also play with it yourself online. Project tensorflow.org. Super fun. Can I figure out how to do this full screen? That's fun. Maybe. Random buttons. Come on. That was not it. That was really not it. But we can do it like this. So, as you saw, it represents concepts in a whole bunch of different interesting ways. But, well, how do you learn it? You can take different inputs, actually, in the first place. What we've seen now, right, has just been words. But there's nothing stopping you from doing images, for example, or sounds, and so on. And obviously, doing this sort of thing would allow you to also match between these different modalities. So you could have the same model which embeds both images and text and audio into the same embedding space. And then hopefully what you get is that you get cats, the sound of cats and images of cats to wind up sort of in the same space. And then you can do really cool stuff. And I won't tell you what it is, at least not yet. You can see if you figure out something cool while I talk, because I think you're starting to get a hold of what we're doing here, right? But one really important thing to keep in mind if you ever want to use these models to something is that they are very objective dependent. So I haven't talked anything about how you train models and neural networks today, because with foundation models, we don't really need to care. However, it does matter for their performance how they were trained. The ones we've seen here have been essentially trained with like fill in the blank. So imagine you take a sentence like, the cat is hungry. Then we remove the concept cat, and we try to make the model fill back in cat. And then it should learn a representation of cat that means that it fits well there. And if the dog is hungry is another sentence that we sort of make sense, then cat and dog should wind up being similar in this embedding space. This is like the most common strategy, at least for word embeddings, to use these days. You can also do other stuff like just counting the neighbors is also really common for older systems, especially for words. For images, you have a really similar concept where you do image repair. Essentially, you can do what we just did with diffusion networks, right? Except before you recreate your image, you force it to be really small. You need to compress the information, and then from this compressed information, you get to rebuild the image. Then this compressed set should represent as much of the image as possible. But you can also do all other fun sorts of image repair, like you can remove just subsections of an image, you can denoise it, you can do super cool stuff. And really, these two are sides of the same coin, right? The first one is really sort of like text repair, and the second one is image repair. But you can also do entirely different things. The coolest of which is contrastive learning. Because imagine you wanted this embedding space which had both images and text together. You can't really like have the same model try to repair a sentence as tries to repair an image and expect it to wind up being anywhere close in the same embedding space. What we do in a contrastive setting is instead that we have pairs like this. For example, we've scraped the internet, as you know, any good AI company would, and we've grabbed a whole bunch of images and these alternate captions for the images, which tell you like, this is a dog or whatever for blind people and so on. Now we have a pairs of images to text. So instead of trying to repair either of them, or in addition to doing that, we just say, hey, these two should be really close in the embedding space. And we also tell it, everything else, that should be far away. And by doing this, we get a single embedding space which shares these modalities. There's also a lot of other more stupid stuff you could do. These are like the most common. But if somebody's made a mistake in their training or so on, for example, if I train it on customer reviews and I just try to predict, is this a good or a bad review? Then the only thing that's going to be caught in your embedding space is just how positive and how negative is this word? And how useful is it for the task of determining what a review gives? So doing that training task wouldn't give you this nice embedding space we have here, where we see a separation on men and women, for example, unless that happens to be really relevant for how positive and negative the word intersects. So if you use an embedding model, it makes sense to check how it was trained, though you can usually assume it's one of those three, and you can usually assume it's good at what it does. So I promised that there were a few different types. Let's have a quick look. First, I'm going to give a shout out to Kungliga Biblioteket, who actually train AI models. If you didn't know, they do. They have KB-BERT, which is like a text embedding model. You give it text, and then it gives you a small embedding per word chunk in that. And supposedly, it's trained on high-quality data, and I believe them because, well, they are them. And it's obviously specialized in Swedish and Nordic languages. Then we have Quen embedding v3, and there we see that we actually use these ones also in the LLMs, usually, and within the same context. So we saw the Quen family of LLMs before. We also have embedding model families from the same network. And of course, we have the OG and my personal favorite, we have Clip, which is the first one to do this contrastive style training I mentioned. So that gives you both images and language in the same space. So, you probably guessed it. What can we do with these models? Audience, come on, I believe in you. You should figure out the pattern. You can think while I talk. I believe in you. Mike?
Oh,
thank you.
I didn't see you.
My brother likes to play these strange word games like Wordle and Contexto. And some of those games are based on similarities between words, and they often use embedding spaces to do that. It's an example of.
I think that makes so much sense. I've been wanting to do this. I want to beat code names, so I can play it with myself. Or so I don't need to play it at all, I guess. I can practice my competitive code names. I mean, you need to get good. I am willing to stand in silence for quite a while.
I know it's used to map out a code base, like an embedding model is used to index the code base that you have so that the LLM can read it or get a sense of what your existing code base can do.
Yeah, I think that's perfect, right? And that is the sort of thing you do in like RAG, for example, which is retrieval augmented generation. You can do it a whole bunch of ways, but the most common is doing exactly what you said, right? You embed your whole code base or knowledge base or whatever it is you have. And then when you want to answer a question, you can find stuff really easily by using vector databases and finding stuff that's similar to it. So I think that would be really sweet. And for the third one, I'm actually going to say it myself, and we're going to actually backtrack to this super cool library idea we had before. And I mean, if you have a library, right, you probably want to search it and find stuff in it. I know that's half of the reason why I use Google Photos. And if you have like Clip, for example, added to it, you could search for text and find similar images and so on within your cool library that you set up previously of all your things. So super convenient to have embedding models for a whole bunch of stuff. With that said, we had a thing?
Did you have a question?
No? Oh yeah, I also forgot to mention, you can have the slides later if you want. It'll be a QR code and things. Yes, so let's move on to our next set of models. These are segmentation models. And what these do is that they segment things. Who would have guessed? It's in the name. But they split up images, essentially, into different parts, different segments. And what these segments are depends on what model you're using. Right here, we're seeing a recent vacation photo of mine from when I went to Cambridge to visit the university there for a bit. And we can see that it has managed to see these different people in the photo, and it has marked each of them for me. And at the same time, it's not marked the trees or anything like that. It even managed to find some people in the background that I'm not sure I would have spotted, to be honest. And this is the essence of what the segmentation models do. And there are two main categories here. You have single and multi-instance ones. What we're seeing here is I was going to tell you, but let's do a vote. That's more fun. We have two options. I haven't told you what either of them are yet. You're still going to get to vote. Everybody who believes it's single instance segmentation, raise a hand. Everybody who believes it's multi-instance generation, raise a hand. Multi-instance wins and multi-instance is right. So I'm guessing what the vote for single instance was going for is that these are all people, and the only thing it segmented was people. And that would have made total sense as a nomenclature, but it's not the one we're using. Instead, the single and multi-instance definition is if it sees only that there is people or that these are different people. So what we're seeing here is that this guy is different from this one. If we had a single instance classifier, it would just say, hey, these are people. And then you get to figure out yourself if they're the same person or if they're different people. And this, of course, goes for everything beyond people. It goes for cars, trees, fish, whatever it is you're looking at, right? And depending on your use case, these might be differently useful. But again, just like before, we have this in a whole bunch of different options. What we're seeing here is object identification, right? It's finding different objects in the image. In this case, different people, but we could find different other things too. We can also do other stuff. We can do depth estimation, for example. I've used that in a few projects and it's super neat. So that essentially lets you convert the 2D image like this into pseudo 3D. Not the same kind of 3D as before with the generative models which guess, but here we retain the model and we just add a depth to the image, as if it would have been taken with a LiDAR camera or something like that. We can, for example, do background estimation. So like what in the image is background in the first place. And segmentation models are actually like so many options. We can do really cool stuff. One I found which was among the most popular on Hugging Face when I looked was like flood segmentation. So if you want to find floods in like satellite images, you can segment floods. So whatever strange use case you have, hopefully somebody has trained a model to segment it. Because hopefully you're not so strange as you think you are. I mean, floods is represented, come on. Yes, let's have a quick look at a few different options here. We have SAM, which is like segment anything model. It's made by Meta and it's like the model sort of for segmentation if you want to do most of it. It's the one that I use for this photo and it's even interactive. So you can, while you use it, you can say, hey, I want this point, and then it will figure out, hey, I think this is the object you're going for, and then you can add more points to clarify, essentially. Or you can do what I did here and just search on text. SAM also somehow can generate 3D objects. I'm not sure how it does it, but it can, so that's fun. We also have two more models here to shout out. We have one for background estimation and one for depth estimation, because I think these are two really useful categories. You should, as said, be seeing the pattern. So what can we do with these segmentation models? Good. Yes. Answers.
One useful thing would be for self-driving cars to, as long as you have a consistent ID frame to frame, like you can track cars or pedestrians or anything else like that.
That makes perfect sense. And for these new ones like SAM, we can even get this consistent ID across videos. So you should be able to just plug and play that into your local self-driving car.
I'm going to continue with the politics things and replace voting.
Okay. How are we replacing voting?
So basically you have some sort of data space and you categorize, you segment which party that you belong to. So that way you don't really need the voting process, it's already there.
Okay. So I'm getting it. Okay, so we have like an embedding model that adds people to like political compass orientations. Then we take their votes, we set up a segmentation model on top of that. We segment the space, then we just take the population, we put it in there, and boom, direct democracy solved, right? Yeah?
People tend to change their minds, or
Well, I mean that sounds like a future issue. We fixed that in revision 2. After, of course, my robot party has been selected, then we'll figure it out later, you know.
I guess which I've spoken to you with, Elliot. You can identify fish. Count fish, for example.
Yeah, if you theoretically here were to have a project where you wanted to count fish, this would be a really good way of going about it.
All right, so if we combine it with other like identifying factors, other models, we can also have both malicious and kind of beneficial ways of using segmentation to maybe identify patterns in how people move and if they're ill or if they're part of a certain ethnic group or political affiliation due to like tags on their bags or whatever. We can have like social scoring and social manipulation basically. Also, if we combine it with like real world robotics, also one of the different models we can use is how we automate the world with AI. The world can change depending on like who you are and what you act like.
Yeah, I think that's totally true. And we're working on this dystopian angle here. I like it. Yeah, I think we could do something like this, right? I mean, you have models already which can identify faces and clothes, separate those from each other, and then you can obviously operate on this to identify whatever ethically unsuitable features you want, then you can do scoring on this, right?
Could you take on Midjourney? If I have an image, I can make it like a small video clip. It just kind of guesses. If I took an image like this, like the one you have there, could you create like a VR where you could actually go inside the image? Could you do that with segmentation models?
That
Use
is
it for a virtual reality type.
yes, you could do something like this. So you have the depth estimation ones, which I mentioned, right? You could do that on these, and then you get a really cool like depth-wise of it, and then you can move around in that scene, I imagine, and it will be sort of like abstract in a way, right? Another option, if you want to do the 3D stuff, is if we go back to these diffusion models and we look at the 3D diffusion models, and you use one of those instead. And perhaps if you want to do it in combine it with segmentation models in some cool way, you start by segmenting out all the people and you replace them with suitably horror generic monsters. That could be cool. Or anything along those lines. But I think absolutely could do like walk-in photos. And that is actually super sick. Cool. Happy to see segmentation models getting so much love. They're very useful. It's a reason why, saving the best for last, right? Or at least almost last. Because the last thing we're going to do is we're going to cheat. And we're going to talk about symbolic solvers, which aren't like machine learning models, but they belong in this sort of the first category on the bottom left there, the least AI category that I'm including in the presentation today. And they're also what I do my research on. So, kind of biased here. What these do is that they solve some form of representation. That sounds super abstract, and that's because it is. And that's because there are a whole bunch of these different types out there. So we're going to use a small example from my field of research, which is called planning. And imagine we are NASA, and we want to send up a Mars rover, and we want it to do cool stuff. But while it's doing cool stuff, we don't want to send too much information to it and back and forth because, well, it's on Mars, and that's not so convenient. So far, we don't have Ethernet for Mars. And while it's there, therefore, I want it to act autonomously, and I want to be able to do things by itself, but I still want to be able to control those to some degree, and I want it to be able to do safe, well-chosen things. So I start by having a bunch of engineers design a model of how the rover operates. It's able to move forward, turn right, turn left, pick up rocks, and whatever else Mars rovers can do. I have actually no clue. I guess they can charge batteries somehow. And this results in a representation showing what the model can do. Then at runtime, we combine this with some user input. Perhaps we tell it to, hey, you see that rock over there, Mr. Mars rover? Please go over and analyze it for me. So instead of remote driving it, we just tell it the objective. This is combined into a joint representation. It knows where the rock is, it knows where itself is, it knows what the goal is. I want to have analyzed that rock. Then we take this representation, we shove it through a solver, and what the solver does, we don't really need to care about, right? We treat it like a black box. And then out of the solver, we get a plan or a solution. In this case, we turn a few degrees, we drive a bit forward, and so on and so forth. And by doing this, we actually get guarantees. We can trust that the model will do what we told it to do. I could give this to an LLM, right? And just tell it, hey, figure out for me, okay, thanks. And that's been part of what I've been looking at in my research. And a year and a half ago, they messed up stacking 4 blocks on top of each other. They would cheat and do things the robot couldn't do. These days, they're better, but I'm not sure I would trust better still with a Mars rover. They're kind of expensive. And whatever task you're doing, they are also oftentimes smaller. You can guarantee not only that you get a valid solution, you can guarantee that you get the best solution. You can try to get some, several unique solutions or anything along these lines. So by operating in the symbolic space, we get a lot of different guarantees and different ways of doing things. It also, of course, can be combined with things. And this was when I was going to point out, if none of you had figured it out, that we can combine these different foundation model stuff with each other, right? Of course, we did good. So you managed to figure it out. I'm proud. Good audience. For example, LLMs is the obvious solution, right? And that's part of what I'm looking at in my research, where perhaps we do this part with a human and we do this part with an LLM. And that way we know that any choices it makes are going to be based on actual robot dynamics, even if it might have misunderstood what your goal was. But we can still have faith in some parts of the model. And by doing this, we can solve a lot of really cool problems. Before, I've been showing you different specific models and what they do. Here I'll instead quickly mention a few different types of symbolic solvers, which do different things. Planners or PDDL planners do the sort of thing we've been looking at here. You describe what actions you can take, and this can be something like driving a Mars rover, or something more abstract, like exploiting a security vulnerability in a system. And then you explain it how it is right now, and how you would like it to be. And then they try to find a path to get between there, and if they find one, they'll give it to you. If not, they prove that your system is unsolvable. And I mean, that's not something you would ever get from an LLM, right? For example, you can never prove things with them. Getting more into the general and philosophical space, we have SAT solvers, which just take in logical representations, like where you say that X1 represents me having an umbrella, and X2 represent it raining outside, and maybe I want to guarantee that if it's raining outside, then I have an umbrella. And then we give this to the SAT solver, and the SAT solver finds a solution for us. In this case, maybe saying, bring an umbrella, dude. And by doing this, we can solve a whole bunch of different logical solutions, which we can map into this space. Last one, I'm going to give a shout out to our theorem provers, which can just show whether not something like really abstract mathematical thing is true. And the reason these are interesting is that if I recall correctly, then I should have fact-checked this before I'm spreading misinformation to you guys. These were what was used in the recent set of LLMs, which managed to win like these gold Olympics and so on within math reasoning. So what they do is not that they actually solve it themselves, but they model the problem and then they use solvers to help them solve and prove parts of the solution. And by doing this, we can do spicy things. So I've been kind of cheating, right? And saying things already. But anybody want to point out anything else cool we can do with solvers like this? Questions are also good.
So this solver thing, is that a neural network or what is that?
So generally speaking, they're not neural networks. Instead, they're usually like hand-built software, which does some form of like theoretically proven optimal or sound algorithm. Like a planner usually runs some variant of A star, if you happen to know that. It's a graph search algorithm. But it's also very possible that these solvers internally use some form of neural networks to, for example, estimate what seems the best. With a SAT solver, for example, you need to make a lot of choices, like, do I make this variable true or do I make this variable false? Do I make Elliot bring an umbrella or do I make him not bring an umbrella? And initially, you might not have so much to go on, so you need to guess. This guessing can be informed by neural networks, which you've trained on other stuff before. But usually, even if you have them, you can maintain these guarantees that you'll still find optimal solutions. So yes, sometimes-ish.
So I don't know if it's correct, but it sounds like you could use this to play board games.
Yes, you can, and it's pretty cool. So if you look in the symbolic planning community, we have a lot of our like standard testing consists of board games and such that we report it into this language, and then we see, can we solve this or not? And I also suspect that, I mean, a lot of companies which design puzzle games, especially board games, use stuff like this internally to help them develop their games, as well as to help them check that, hey, you can actually solve this, and the best solution is 173 steps long or whatever. Recently saw a puzzle game like this, and it drove me a bit insane trying to figure it out.
I just wanted to get to politics before him. So I have, since it's based on propositional logic, the SAT solver, you could obviously, arguments are famously just, you validate them with propositional logic if they're sound or valid. So you could use that to make arguments, and you can remove the politicians and then just use a SAT solver or something.
That sounds safe. So, okay, so we managed to remove, what have we removed? We've removed the voting, we've added in the social scoring element, so we can get really good representations there. Now we're removing the politicians as well. I'm liking it, yeah. So I mean, we can automate the whole debates, right? That sounds pretty cool. Let's do it. I'm all in favor.
So I'm thinking about, when you have automated browsers, you give them a task. Can this be a tool for solving that? That you give them a task, they look at a website, they find what elements are necessary to like complete the task that you're presented with, and it finds ways to do that.
I think for sure, right? So I think that's a brilliant way of using this technology. For example, you could do like some vision processing, right, to do this step, and you have this, like what you can press on and so on, and how websites generally work. And then you can get really good set of instructions for a human to follow, or you can just act it out automatically, right? So, soon we don't even need to use our own browsers anymore, right? Sweet. All right. So I mentioned it before, and that was the last model I was going to go through. I've got some small closing remarks. First of all, this was, as I mentioned, a very quick overview of each of these 5 different foundation models. There are probably other things you could have brought up as well as different types of foundation models. And it's also possible that I could do just a full workshop evening about each of these models. And that's actually something I'm considering doing. If I do, these are going to be a mix of a presentation style like this, which combines theory, intuition, and the reasoning behind the models, along with more practical tryout sessions where I hope people have computers, we bring them, we try to actually use segmentation model or whatever and see what we can do with it. If you're interested in that, please fill out this form here to just give me a vibe if people would be into it, because it'll take work for me to do, and I would prefer that people want it, right? You can also get informed if I actually do it by filling that out. By filling out that form, you also get access to the slides from this presentation, including the models and all of that which we mentioned. So if you want them, you can fill that out. If you have any feedback to me on general presentations and stuff, I love to hear that. Tell it to my face, or again, form, great place to be. And lastly, do please reach out and keep in touch. I added my LinkedIn there. Feel free to reach out there, or in whatever way. You can probably Google me and find me. But with that said, I hope you found it interesting. I'll be sticking around a bit longer. I know a decent bit of you, and you're all cool. So feel free to also stick around longer, mingle, and hang out for a bit. Thank you very much for coming, everybody. Yeah, do we want to do joint questions, actually? I think we mentioned that before, Aaron.
Yeah, we can take some questions now if you have it, or else I know you're going to be sticking around. You can always talk to Elliot. But is there any questions you really want to ask right now? Yes, perfect.
So I'm kind of lazy, and been browsing around, trying to use different models. But is there something to help me as the lazy guy to evaluate models in, like a general way?
Yes, good question. Two good suggestions for you. The first is that especially for these like more popular tasks like LLMs and so on, you have a bunch of leaderboards, right? You can look at them and hope that they've not trained too much on the testing data, and what does there probably does well.
Yeah, and just like a comment on that, I come to understand that different models, when I try to run them locally on my semi-powerful computer, has very different performance in terms of how they scale with the different context inputs and yada yada. So even though I sort of like one model, given the benchmark tests, I don't like using it because it's restricted in my context and so on.
Yeah, that might be an issue, right? So part of that is that bigger models are usually better, and that they just make better estimates. Part of it can be that they're just poorly optimized, especially for like LLMs. There's a lot of recent stuff that you can do, which not everybody does. One thing which is sometimes possible to do, like on top of the models, is to do this quantization, which I mentioned before, where you like reduce the precision in the model. Sometimes you can do that after they've trained it. You can do it yourself. Usually you can. Hopefully somebody else has done it for you and you can take it from them. That is one way of getting up to speed. The other good suggestion for how you try out models is that especially Hugging Face, which is like the library of these pre-trained models, sometimes offers what's called spaces, which are like interactive test environments where you can try out models which have been set up by other people. If you find them, that's by far the best way, in my opinion, of testing models, because then you can really test it on your own stuff, right, in the same setting you'd like it to be. But it's not always available.
Okay, anybody else questions for Elliot? Yes?
So I've been looking at things like Cosmos from Microsoft, if you've seen that, which is basically like this mother AI that has a lot of different smaller tools, specific tools. I'm guessing kind of like the foundation models that you've showed us today. So what would be your like biggest possibilities that you see when we can have like one major model which keeps track of all of the tasks that need to be done, like the processes and sub-processes, and pick the specific tools for each assignment, and then collect it and create something better?
Yeah, I think like this is a really good way to go. Essentially the best way to go, probably. And I think it's the way that we see a lot of these like tools working behind the scenes as well, even though we can't see it, right? I mean, looking at like ChatGPT, if you're using that as well, right, it has a small tool selection available to it. And we also see all this development with MCP technology where you can design your own like LLM available tools which the models can use as needed. I think using specialized tools like this makes a whole lot of sense, because we want usually the generality and the ease of use, which we see from language models and so on, but they have a whole suite of issues like hallucinations, lack of guarantees, and so forth. And combining them with tools that aren't LLMs, be they like chess solvers, theorem provers, or whatever else you find. Internet search browsing, for example, is a common one. That really unlocks a whole new set of things you can do in the first place. So I think it's the way to go, and less horrifying than making mega smart single systems.
Okay, who's next? Going once, twice. Okay. Thank you, Elliot.
All right, thank you very much, everybody, and let the mingle part officially begin.